Now, for the math purists out there, I understand the equivalent of what I've done is that I said it's infinitely long, here's the last one, which causes issues in certain math disciplines. However, in physics, go with the spirit of it.
3 over C.
Close,
Just 3C.
not 3C.
They're in series, right?
They are in series. You forgot a final step, unless I misheard. You said 3 over C.
Barrett.
No,
Oh, it's sealed.
yeah, you have to flip it at the end. 1 over C plus 1 over C plus 1 over C is 1 over, well, I'll just call it C sub 1. So the equivalent capacitance here is 3 over C over 3, or 1/3 C. Now that's going to be in parallel with the capacitor, basically that next unit capacitor. So if I have another capacitor, or another set right here, my equivalent capacitance, well, that right there, this is in parallel with this structure of 3, so this whole thing becomes 4/3 C. So now I can treat my end cap here as I've got that C, that's 4/3 C, that's C. In series. And what's the equivalent capacitance? Or how would you find it?
Would it be 1 over C plus 1 over C plus 3 over 4C?
Okay, so, well, 1 over C2
Yeah.
would be 1 over C plus 1 over C plus 1 over, 3 over 4C, which is 11 over 4C. So the equivalent capacitance of this 2 unit would be, well, the reciprocal. In decimal form, that's a 0.333 repeating C. In decimal form, what is this?
36, 36, 36. 36 repeat.
Now, if it diverged, then the answer is infinity, but I'm gonna do one more just to show that as you add on these end caps, or the next MER into it, then it's converging. So we'll do one more. So I now have this structure right here with an equivalent capacitance of 4/11 C, and I tack on the next bit. And so this is 4/11 C, that's C, and that's C. So I'm putting on those 2 side capacitors every single time. And what you get? Oh, there's a mistake there. This right here is 4/11 C, but I'm not tacking on just the side pieces. I'm tacking on I got that, and that. So first off, let's deal with that. And so I'm just adding C to it. So that actually would be 15. 15/11 C.
Would just be 4/23 C.
Say it again?
4/23 C.
Something doesn't seem right about that.
I ended up with 15/41. Yeah.
Which is,
3658.
all right. So notice that we went from point 3 repeating to point 36, 3636 to point 3658. The gap is shortening as we progress, at least with these three, and it would continue to close in. So if this does indeed approach a value, then at some point, the difference between what we calculate and the actual equivalent capacitance is almost negligible. So I'm going to take it down to the last two. And I mean by that is I've got the side capacitor across the other side. And then over here, so that's C, C, and C, is we have something that is so close to the equivalent capacitance, we're just going to say it's equal. Good enough for physics. Just because it's a pain to write, I'm going to write this as E, just because I don't feel like writing the subscript. So these two are in parallel, so I've got C. This is C plus E. And that's C. And to add these up, I have 1 over C plus 1 over C plus 1 over C plus E is equal to 1 over 1 over E. Because ultimately, my equivalent capacitance, the difference between the equivalent capacitance and this value right here, negligible. So let us solve for E. Get the common denominator, so this would be E times C plus E over C times 2, because I got 2 of them, plus this would be CE, so C plus E, this would be C plus E, CE, is equal to C plus E times C over C plus E. I guess I could have saved some writing by just multiplying everything by C, E, C plus E. All right, so now I have this top here, so I'm going to distribute. So I have 2EC plus 2E squared plus CE is equal to C squared plus EC. Those cancel out. I'm solving for E, and so I got an E squared, so I'm dealing with quadratic. So I have 2E squared plus 2CE plus C squared is equal to 0. a little quadratic formula. So my equivalent capacitance is -2C plus or minus the square root of 4C squared minus 4 times 2 times C squared. Oh, that should be negative C squared, divided by 4. Well, I've got C squared that I can factor out square root of it. So I end up with C times -2 plus or minus the square root of, that's 8 and 4, which is 12. The two negatives become adding over 4. And that's a 12, not 18. And so what are my answers?
Point 366025. And negative 1.366025.
All right, so what is the answer then? Or what is not the answer?
The negative one.
Yeah. I can't add capacitors together and get a negative capacitance. I guess negative capacitance, it would reject charge, force things back into a battery, I'm not sure. Anyway, so we end up with that. So I'm assuming that we had gotten up to 0.3658, so we're approaching it rather quickly. But I find, well, in the past, this has brought up most questions. But it's a sort of a conceptual leap to have the answer incorporated, well, basically to have those E's like that, to have this answer incorporated into the total. Ooh, PJ.
When we found a common denominator, and then we just started using the numerator.
Yes.
After distributing.
Yeah.
Why is that?
Technically, I took more steps than I should have. What in essence I did is I multiplied everything by the common denominator. So I got rid of it, but also, if I have a common denominator and I add fractions, it becomes this plus that, since they have the same denominator. And then I can multiply by the common denominator, those all go away.
Oh, I forgot there was an equal sign. Okay, that makes sense.
Yeah, there's the equal sign there. Other questions? This was problem 82 from chapter 27.
Back over here, to get the 15/11C, yes. So it was the 1/C plus 1/C plus that 4/11C.
No, we got the 15/11ths because I've got my series here. So I'll look at just this section right here. This part right here was 0.3 repeating C. Then when I add this to it, because it's in parallel, so if I get this far, this is 1.3 C. And then I add then I bring in those two, and I get 4/11 C. And then I add that one to it, and I get 1 4/11 C. That's 15/11.
Yeah.
That's where that comes from.
Okay, I see.
All right, I'm going to say I'm officially done with 27. You have the test next week, so I'm going to say that 27 stuff will be the week after. February 28th. Oh, happy Valentine's Day, everyone. So, homework quiz 27, master set 27. All right, so let's talk about current. In current, when we're dealing with electrical current, or as we'll probably just generally call it, current, we're dealing with charges moving. And so current is defined, current, the symbol that we use is I, and it's defined at a specific point as dq dt. If it's constant, we can get away with delta Q over delta T. Now, we've got to be careful with this, because normally when you have delta there, we're talking about a change. But in this particular sense, what we're talking about is the amount of charge that passes by a particular point. So if I have a long wire here, I look at this point right here, I see how much charge is passing by it, or the total charge that passes by it within a certain amount of time, do some division, done. Let's explore this a little bit more. I'm going to take this equation here and I'm going to split it up. So that's the same as dq dx times dx dt. And what's dx dt?
Velocity.
Very close. Scalar. Speed. Now, when we're talking about the speed of the current or the charges that are flowing, recognize that if I have a wire here, a charge is not just going to go shooting through the tube. It's not like I've got a vacuum tube here and I'm sending a particle through most of the time. High energy physics, you do have that, but if we're talking about a wire in the wall, we're not dealing with that. Then we have a particle that comes in, let's say we have an electron flowing in, it's going to hit something because there's atoms in here, or interact with it, and it's going to bounce and it's going to hit something else and hit, so it's, you know, it has a tendency to not move in a straight line. And this one actually came outside the wire. We'll pretend that did not happen. And so when we're talking about the speed, we're talking about the distance that it travels in a certain amount of time. That is just going Saturn. And so the speed is the drift speed. And so we have this dq dx times the drift speed. And I'm going to put a serif there because at some point we're going to have three different v's, and so I need to differentiate them. All right, so let's think about this charge that's passing through the wire. Now I am going to have more than one electron that's moving, presumably. If only one electron's moving, then it's probably be close enough to an insulator. Somewhere there's going to be a marker that I find dark enough. Nope. Okay. So I'm going to let capital N be the number of mobile charge carriers. Because in a conductor, not every electron is fair game. They only have it's the electrons in the outer shells that are the ones that actually have enough energy to move freely. And so I can define n, lowercase n, to be the mobile charge carrier density. And it is the number of mobile charge carriers per unit volume. And I put the serifs at the top of volume. It's supposed to be a V. So the charge that's going to be flowing here would be, well, Q times the number of mobile charge carriers. So my charge is going to be the charge per carrier times the number of mobile charge carriers, which is just going to be, well, capital N is little n V, so this is Q in V. Well, Q is the charge of usually the electron. N is a charge carrier density, which is material specific. The volume is the thing that's going to change. So dq dx just going to be Q in dv dx. That's again changing volume with respect over volume over x. So if I think about, I've got we'll just treat it as a cylinder here, with a width of dx. My volume is dv, so my volume here of dv is going to be dx times the cross-sectional area. And so plugging this in, I have Q in dv dx. And dv dx is just the cross-sectional area. So I have Q in